Okay, we can go ahead and get started. Are you excited?
Yes.
Well, I am, and you'll be very pleased to know that Max talked me down, and we took out a question that we were planning on putting in. So be sure to thank him in any way that you feel is appropriate, but not in a way that might influence his evaluation of your exam. So no cash, please. Those should go directly to me. All right. On the agenda for today, I do want to talk a bit about some additional statistics before reviewing the contents in the exam. And what we're going to be focusing on, so last time we talked about the t-test and the z-statistic and the z-test in cases where you have a single measurement and the mean is known. And I'll review a couple of concrete examples so you sort of know the scenarios in which that might arise. And then we'll move on to the t-test, the z-test, and the f-test for a difference between two random numbers. So let's just sort of recap from last time. Come on, you can do this. Let's see, I probably want... this will be a good example for a t-test for a single measurement. One in which you know that you have a standard that you're assessing and you're asking whether or not this experimental measurement is within tolerance of that targeted goal. So the underlying mu is known, in this case 6.15, and you're asking what's the probability of this x bar being described by a distribution consistent with that. We'll get there. Yay. Okay. I'm not going to work through this. I'm going to go through it very quickly. I just want to put this up to illustrate the kinds of scenarios in which this might be applied. All right? No, I don't want to keep that, actually. So let's go back to today and ask what happens if we're now evaluating the difference between two experimental measurements. And we're going to start with a hypothetical that you're not likely to encounter experimentally based on the z-statistic. So if we know sigma in advance, how do we evaluate whether two experimental means are within tolerance of each other? So the null hypothesis x bar 1 and x bar 2 come from the same PDF. That's the null hypothesis. The alternative hypothesis means they are statistically distinguishable. The null hypothesis here would mean these two x bar measurements were statistically indistinguishable from each other, which is another way of saying, statistically speaking, they come from the same PDF. They cannot be distinguished as coming from separate PDFs. It's really the more proper way of saying that. Does that make sense? Okay. All right, so if we know sigma in advance, in practice we're going to figure out how to replace this with s in a moment, but if we know sigma in advance, then what we'll define d as being the difference between x bar 1 and x bar 2. And what is the mean of d if these come from the same PDF? Well, that's going to be 0. And the sigma squared of d is going to be sigma squared x1 bar plus sigma squared x2 bar. All right? What is sigma squared of x1 bar and x2 bar in terms of the probability density for x? Well, we can write this sigma squared d is going to be sigma squared over n1 plus sigma squared over n2. Right, because variances of random numbers add. So if sigma is the variance in x, what's the variance in x bar? it's going to be sigma squared divided by n. Square root n reduction in sigma. Everyone okay? No, you're not okay with this one. All right. So if we have sigma as being the distribution in n, maybe we'll go over here. We'll make a new one and even color it differently to distinguish it. If sigma is sigma squared is the variance what is the variance in x bar? And this is one of the ones we worked through previously. If sigma squared is a variance in x, the variance in x bar is going to be sigma squared. Let's see, the variance in x bar will be sigma squared 1 plus sigma squared I, j, sigma squared k. Is n sigma squared x, right? So therefore, sigma squared x equals 1 over n sigma squared x bar. Oh, yeah, there should be one of those. Thank you. So it's a summation over all of the sigma squared values. And since they're all the same, they're just sigma x, and sigma x is just that. So that's where you get this 1 over n scaling. And so that's where the n comes from in this expression right here. Does that make sense now? Okay. So then if we look at, we'll keep it blue. Sigma d is going to be the square root of, let's see, this is really 1 over n1 plus 1 over n2, which is going to be n1 plus n2 over n1 times n2 times sigma. I skipped a step there. Hope that's okay with everybody. If not, we'll do it this way. That thing in red there is just 1 over n1 plus 1 over n2. Common multiple. You make a common denominator of n1 times n2, and you end up with that expression. Yeah.
What's that last sigma there?
That is sigma for x. I just left off the x because I'm using the notation in the lecture notes. Everyone okay? All right. So this is fantastic if we know sigma in advance. In practice, what if we don't? Oh, I should actually I should continue on with this before I move on to the next topic. So if this is the expression, before we get to that, if this is the expression for sigma d, then what is the t statistic for evaluating confidence intervals? And then that's going to be x1 bar minus x2 bar over sigma times this scaling. Actually, be n1 times n2 because it's 1 over this. And all we have done is taken our previous expression and rescaled the standard deviation by this factor of n1 times n2. Well, actually, we rescaled the standard deviation by n1 plus n2 over n1 times n2, but it's in the denominator, so we bring the inverse of that into the numerator. Yeah? But otherwise, it's exactly the same thing we had had before. If sigma is known. Okay, and then the next question, if we do not know sigma, donut. Okay. I think I'm going to have to switch back to red just to avoid confusion. If we don't know sigma in advance, we estimate it using S. Okay, and so we're going to define what is S going to look like, or S squared going to look like, if I'm taking two sets of numbers and adding them together. What might not be obvious, but it's going to look like this. 1 over n1 plus n2 minus 2 times the summation of I xi minus x bar 1 squared plus the summation over j xj minus x bar 2 squared. Right? Because I'm taking I'm repeating this operation twice, and I've got 2 degrees of freedom that I'm pulling out, one for x bar 1 and one for x bar 2. People are still writing. I'll let you write this down before I go on to the next step. Yeah.
Do SI and SJ from different tests or from the same test?
So we have our x bar and our s bar. We have an x bar for population 1 and an x bar for population 2. We're calculating effectively something that looks kind of like an s squared for population 1 and an s squared for population 2. And then the real question is, how do we handle the scaling of the 1 over n minus 1 factor? And that's why we're calling this a pooled variance. I'm going to put a subscript p on this for pooled. And what we'll show is we'll be using this as the definition of p. What we should get for something where we're combining these two experimental standard deviations. The term we're going to want to use is going to look like this, and then we're going to want to relate it back to S1 and S2. Yeah.
So I are the individual measurement, or XI is the individual measurements for the first population.
Yeah.
And J is for the second.
Yeah. The population for 1 and the population for 2. Those are, so that first summation is evaluated just from the measurements in the first batch, and then the second one is evaluated using just the measurements from the second batch. Make sense? Okay. So what does this look like? Well, I'm going to rewrite this in a slightly different way. This is going to equal 1 over this should be an n1, n2 minus 1, I'm just multiplying each of these by 1. Yeah.
Why?
That's just the question I was going to ask you. This is perfect. Why do that? I'm sorry? Yeah, this is the definition of s squared 1, and this is the definition of s squared 2. So now we can substitute those back in. That's the whole point of multiplying by the 1, by n minus 1 over times n minus 1 over n minus 1. So if we do this substitution, what we'll end up with is s squared p for the population is going to be 1 over n1 plus n2 minus 2 times yeah. Yay. All right. Now all we do is take this and substitute in the z-test example, we'll substitute our best estimate for sigma based on SP. And now we have a z statistic, or a parameter here, that looks like the sum of the two variances, but with all these rescalings of n and n plus 1 and n over 1, and all these sort of bookkeeping details in terms of the accounting for the individual n's. But it really is just rescaling the standard deviation in the denominator to have some weighting for the two different experimental standard deviations. Does that make sense? So it looks more complicated than it is in terms of just the sheer number of n's and the sort of these factors that sneak in. But it's the same essential idea as just this. All we're doing is just sort of we have to add these additional correction factors in to account for the fact that these are the sum of two different experimental standard deviations pooled from maybe 20 measurements in one case and 5 measurements in another, but it's still the same general idea. Make sense? Hopefully?
That's
I'm sorry?
that's good.
Yeah, this is for the t-test. This is basically now going back and asking, if we go back to the very beginning, the z-test was the first one where we knew sigma in advance. And then the t-test is the one we just did.
So the z you're solving for t as well?
Yeah, actually that was a mistake. This should be z. Thank you. Got ahead of myself. Good thing I have the both of you here. Okay. And then this is actually t. So let's look at an example of this. It's easiest for me to do this with the keyboard on. No, that's going to be up. T-test for two averages. Where are you? Okay, yeah, this would be an example. We'll get to the f-test in a moment. Let's see. But this is, come on. Okay, yeah, this is the example that I want to use. Don't worry about the fact that it says f-test right here. We'll get to the f-test next. This is just the measurements. We're basically taking one set of 3 measurements and one set of 5 measurements and asking whether or not these two measurements are statistically indistinguishable. So that'd be a sort of a nice prototypical example of where the t-test might be used. Okay? Now, one of the underlying assumptions that we didn't really talk about was that if we're applying the t-test, these have to have the same underlying variance. And I'm not explaining that well either. Okay, if the null hypothesis is satisfied, then these two measurements come from the same PDF. If that's the case, then they both have to have the same variance as well. The t-test is really focused on the mean, right? It's looking at this x bar 1 minus x bar 2. You can evaluate the t-test as long as these two distributions also have the same variance. So we can actually have a completely independent test just to see whether or not the two distributions have the same variance. And then, if it passes that test in terms of the null hypothesis is satisfied, we can ask whether or not they come from the same mean as well. Does that make sense? So the f-test is asking whether or not these two sets of measurements have statistically indistinguishable variances. Okay? And that's done based on the ratio. Oh, come on. So the null hypothesis is that the two sets of measurements are consistent with a PDF sharing the same variance. So our F is the ratio of standard deviations, with the larger number in the numerator. And then if we wanted to evaluate this statistically, then we have to integrate over the probability density function to see where those confidence limits might lie. And then we ask, what is the probability density function for the ratio of two standard deviations? And it was painful enough to come up with the PDF for S. We now have to come up with a PDF for S1 over S2. But you know what? If we just run enough simulations, we don't have to worry about it anymore, right? That was the take-home message from last time. I'll just tell you that there is a nice, clean functional form for this, and that's in the lecture notes as well. And it looks like this. Ratios of gamma functions. Yay, everyone loves ratios of gamma functions, right? Yeah. At any rate, this is what they look like in terms of the ratios. Now, asymptotically, you'll expect the mean to be 1, right? Because if they do come from the same PDF, then in the limit of many, many measurements, the value of S2 and the value of S1 are going to converge to the same number, and so the ratio will converge to 1. But there's going to be a spread of values consistent with that. And so you'll evaluate confidence intervals by integrating over this PDF for the ratio. Make sense? And so that's what the F test is. Now it's a little tricky because we have to evaluate, if we want to make a table of F values so we can assess confidence intervals, then it's kind of a pain because we have N1 and N2 that don't necessarily have to be identical. So we really need to populate a complete table based on how many degrees of freedom are present for each of those standard deviations. And so we have, for a 95% confidence, we have to have a full table for each confidence limit. It's not like we could for the t-test where we had a table for a whole bunch of different confidence levels. For the f-test, we have to for one confidence, and now we have to populate an entire table. The whole thing starts to be getting burdensome in terms of the sheer number of values that have to be tabulated and looked up, which is, again, why I just say, 10 million simulations is an easy way to get around this whole problem, and just do it on a per trial basis based on numerical evaluations of confidence intervals. It's definitely a viable alternative to looking them up in tables, but you can look them up in tables as well, and this is what they look like. And you can, as expected, the values are going to change depending on whether you have a large number in one or a small number in one. And the value over here is the asymptotic limit when the number of free parameters goes to, or the number of measurements goes to infinity for each of those, and the ratio must converge to 1, and so forth. So hopefully that makes sense. And then typically what you will do is first apply an f-test to see whether or not you can then apply a t-test. And only if an experimental average passes both can you state that they come from a statistically indistinguishable set of measurements. Yeah?
Quick question on notation. What is phi representing here?
Phi is the number of degrees of freedom.
Oh, okay.
So that will be n minus 1 if you're making an average of, if you're using an experimental average and not pooling. So if you're using X for evaluation of the standard deviation, if you're using the experimental mean, then you reduce the number of degrees of freedom, and so phi would be, if for 3 measurements, which would be the minimum, phi would be 2. It's n minus 1. Yeah.
What happens if it does not pass the f-test?
Yeah, that's a great question. If something doesn't pass the f-test, what is that saying? It's saying that the null hypothesis is not satisfied. Therefore, the two means come from, the two means do not come from statistically indistinguishable PDFs.
Okay.
In other words, these two measurements are statistically outside of error of each other, based just on the F-test. And then, so you have basically two chances to assess whether or not these measurements are consistent with each other, one based on the mean and one based on the variance.
So you can run the F-test and it can say no, and you can be like, okay, well, they're distinguishable. They come from two different PDFs.
Yeah,
And then, but if it does pass, then you can run the t-test.
exactly.
And the t-test can say, no, they're different, or they're the same as well.
Yeah, exactly. And that's actually the great example, that's exactly the example that is provided in the lecture notes, where a ratio passes the t-test, or sorry, the f-test, and so then you take these same sets of measurements and apply the t-test, and in this case, it fails that. So you accept the alternative hypotheses that these two experimental measurements are not coming from the same PDF. All right. And it's useful because we're gonna essentially do a t-test on the exam. But it actually turns out to be even simpler than the example I'm providing here, because the t-test on the exam will be based on Poisson statistics, where the mean and the standard deviation are intimately coupled, so we actually don't lose a degree of freedom when we go to Poisson statistics for those. Okay, on to the exam. I'm sorry?
You don't have to.
Well, yeah, but if you have nothing to show for your grade, you have to have something to evaluate, right? Moving right along. I'm not sure if all of you would want that as an assessment based on the feedback I'm getting right now in terms of your level in the. Okay. So I'm guessing it's probably in here, and then there's one. Is it this one?
Yeah. Final? Yeah. I'm used to yeah.
Okay. This professional artwork, you can clearly see, describes an experiment. Actually, this is an experiment done in Dor Benemont's group, where they use a digital multimeter device to image a spectrum onto that mirror array and reflect part of it to a single channel detector and dump part of it. So in this case, we're passing some portion of two Raman spectra onto a single detector. And then the question is, how do you design a filter that's going to maximally resolve between two spectra? So the experiment might be, I know I have either component A or component B that I'm making measurements from. Which of the two is it? And you want to make that assessment with some statistical confidence. And so that's what this question is designed around. And the first part of it is to build up a digital filter. And the way that you're going to do that is by a genetic algorithm. Yeah. So the idea here is that we don't know what digital filter is going to be best. So we're going to start out with a set of many of them, and then pick the two that do the best job. And then we'll mutate them, just like you would genetically, and then build another set of population based on these mutated trials for your filter, run them through the experimental spectra, and find which set of those optimally resolve the two spectra. And then we'll keep doing that iteratively until we have a nice, a high-resolution filter that we can use to to distinguish between one spectrum and the next. Yes?
So the two spectrum we're resolving, are they rejected in the ones that actually make it to the detector?
So the objective is to have the largest intensity for component A and the smallest intensity. Actually, what you're optimizing is the difference. This value right here, oops, that was far too fast. Okay, that delta is mu A minus mu B. So that's going to be the mean intensity on the detector for component A, and minus the mean intensity for component B. So that would be taking your spectrum, imaging it onto the digital micromirror, and then pooling all of those onto your detector and integrating the intensity. So if the mirror passes everything, then you'll have 1 as the mean for a single photon for component A and 1 as the mean for the component B, and you'll have no resolution between the two. So effectively what it's going to do is maximize the throughput for one component and suppress the throughput for the other component. And you'll just try a number of those to map that out. And the algorithm for doing so is in here. Effectively, it really is based on genetics. If this is one of your filters, you keep 2, your 2 top best. These are your 2 filters. The 2 mutations you'll be doing. One is that you just do a point mutation. These are all 1s and 0s, because I'm either rejecting or I'm passing for every one of these. And I'm going to multiply this by my filter to get a sense for what it's going to do on the detector. So if these are 1s and 0s, then you just choose 10% of these and flip them. If it was a 1, make it a 0. So you have, 1%. So we have circa 1% mutation when we're making a new, let's see, what do you call it? A new generation from the 2 parents. And then the other one is you'll swap these 2 segments, just like in chromosomes. And then you'll evaluate that one as a new generation as well. So you'll basically take the 2 best, build a population of many by genetic mutation, run all of those through this assessment to maximize delta, find the 2 that maximize delta the best, and then those are the new parents for a next generation. And then you repeat this for many generations until everything gives a nice resolving power. Make sense? Yeah.
So, just for why we're using the that to determine it, is it just kind of guess and test to eventually get to a good?
Well, it's a guided guess and test. It's really the way to think about it is in evolution, you've got a period of quiet where diversity expands, and then you have a period of strife where a population is culled and diversity is reduced, but the genetic pool that is best equipped to survive does. Yeah. That's basically what we're doing here. Yeah. So it is essentially guess and check in the sense that we could try many different combinations, but the problem is if we wanted to look at the full set of combinations, there's 2 to the 1024 different possible combinations of 1s and 0s in this. And that turns out to be a really big number. So we're not going to try all possible to maximize them on a single pixel basis. We're just going to come up with a few and then let the genetic algorithm optimize for us by mutation. You had a question here?
Yeah, 2 quick ones. Is this how Dora's group generated their filters?
Actually, no. So the question is this how the Benemox group has generated their digital filters? It turns out, and I was talking to Max about this, in writing this question, so this is a computationally, in some ways it's cheap. But in other ways, it turns out there's a fully independent way to do it that you could analytically solve what each one should be. But I wanted to have you go through the genetic algorithm because it's really widely applicable and broadly used in a lot of different applications. So I thought if you had this under your belt, it'd be a more useful toolkit than the analytical solution for defining the single optimal filter.
My other question was the 1% mutation, is that randomly selected?
Yes.
Okay.
Yep, so the 2 random numbers, well, the 2 sets of random operations you're going to be doing in your iterative loop to make your new generation, you'll take 1% random positions and invert their sign, and then you'll flip at a random position.
Are you going to take 1% as a block of 1% or 1% as individual? Okay.
Yeah, individual, choose a random number someplace within this and invert that. So it's a single nucleotide mutation, if that makes any sense. Okay, I'll move on. All right. So once you've got the genetic algorithm working, we move on to question 2, which is this t-test. And that's basically asking, okay, you've built this filter that best resolves two spectra on your detector. What sort of signal to noise do you need to resolve or identify the two components with 99% confidence? And this is, you've got either A or B under the focal point in your instrument, and you need to make a statistical assessment of which one it is, and you want to do it with the lowest number of required photons possible, because that way you can do it in the fastest time. And then how many photons are needed. And this is where it's all based on Poisson statistics. We can use the fact that the variance is equal to the mean. So as long as we know what the mean is, we know what the standard deviation in that value is. And so it's fairly straightforward to evaluate the t-test. There are some tricks to making the whole thing work. And so that's discussed in here. I think, should I say anything about it that might potentially head off some confusion? What do you think, Max?
I would say let's raise a question and think first.
Okay. Yeah. Yes, he's throwing you under the bus this time. And then, do you want to handle the discussion of the third question on the weather prediction?
Sure. This is actually really easy to understand. Basically, for most situations, we assume the sample from a distribution of something is independent from the previous one. But in reality, in most cases, the actual, like in this weather prediction sample, the weather for tomorrow is actually dependent on today's weather in some kind of way. So this one is basically first do a simulation to say what happens if the tomorrow's weather is really dependent on today's weather or the weather on the previous days. And then once you get done the simulation, you probably will find some interesting facts after you finish the simulation. And in the later on question, it's basically you mathematically prove that if you can actually calculate the interesting fact. I won't say too much because I don't want to give you too much information on this. But yeah, I think it's really intuitive to understand. And just for the last part, so let's say what happens if we have an independent draw sample which follows multinomial distribution and compare the multinomial distribution with our simulation and see if there is really a big difference between the independently drawn sample or the sample drawn dependent on the previous samples. Yeah.
So I'll just say a few more comments on this. In terms of the questions and the need for programming, you're going to have to do some programming in the first question because that's going to require, this step is going to require some sort of a program in order to get it to loop through to generate the daughter population. Question 2 is written such that you'll need MathCAD, but you will not need to necessarily write the solutions to this have no programs in them. So you shouldn't actually need to use programming itself. You still need to use MathCAD in order to generate the images and generate the data and display and do the plotting and the histogramming and all that. But you won't actually need to do any programming per se for question 2. There's a lot of analytical pencil and paper stuff on that one as well. And then question 3 is, again, a programming question that you will need to use programming for that. In terms of the format for the exam, far too often we run into issues of academic integrity. And it might be surprising in graduate school that this issue does come up. I'm going to tell you that every time, I think we've caught every person, I think we really have, and it's absolutely not worth it. Because the drop date for this course has not happened yet. In other words, you can look at this exam, fret over it for a week, and then decide, I'm just going to just withdraw from the course. That is a far better option. So it really is. And if your advisor requires you or expects you to take this course, and it's clearly not for you, then just talk to your advisor and work it out. But don't resort to things that might get you in a lot more trouble. And those sorts of things include talking with each other Now we have office hours blocked out, so you can use us as a resource, and we're very forthcoming and helpful in understanding just what the hell we're asking and then debugging specifics of code. So use us as a resource and use anything outside in the world as a resource for understanding the exam as well, but just not each other and not people who have taken the course previously. With respect to the format for the exam in terms of grading, do you want to say anything about making your life easier?
Yes, basically, when you are supposed to turn in the exam on the February 11th, which is a week from today, and then
Do we have a time in there? It's at 10 o'clock or?
10 to 10:15.
10:15.
Yeah,
10 to 10:15.
Yeah, you just bring summarize like Word document printout with basically you just summarize all your results, your plots, and your key like programs on it, and also email me your all MathCAD files to me, and then you can check with me at that time. I can open them and I receive them, and yeah, that's it.
There will not be class on Tuesday. We'll just carve out more office hours for that spot. There will be class on Thursday. So if you're struggling and trying to get that last minute question done, then show up at 10 o'clock and be shamed when you walk in the room. No, I'm just joking. But there will be class on Thursdays beforehand. And we'll collect the exams at the end of class.
We're going to do lecture or problems?
Well, that would be really cruel, wouldn't it? It'll be lecture. What else? Something else? Yeah.
So you mentioned we can't discuss with our peers like the exam, but like could we discuss with our peers like, hey, I don't really understand the F-test. Could you go over that with me? Is that okay?
Well, actually, I prefer not during the exam because it's a slippery slope. What we are planning on doing is holding office hours tomorrow, just for clarifying. So these we probably won't do individual office hours. We'll probably just have like a group, and I don't expect we're going to have any specific questions per se after one day of looking at it. But we're just going to ask, field clarifying questions that people are. Once you look at this and start working it through, you're going to make a list of things that you don't understand what we're meaning for, or what we're asking for. And so we'll probably have a period where once you've sort of knocked your head against a wall for a while, we can help ease some of that pain going into the weekend. The only other piece of advice I'll give, and then I will field these two more questions, is don't wait. We're talking to a group of students who excelled in undergraduate. And the exam, it's going to take a long time. And don't put it off because you never needed a whole week to do an exam before. Just the programming itself can take quite a while. So just give yourself plenty of time and get going on it early. There's a question here.
When is the test going to be made available on the website? When is it actually going to be like up to see and like printed?
Once I get back to office, then I will update the website. Just saying that sometimes you need to refresh your browser in order to make something new show up. Your browser will save the previous page and just show that one. Yeah. So you need to refresh your. Yeah.
Yes. Are those one here? Yeah, I think you
Yeah. Clarification questions. Should we avoid emailing you those, and just because would you rather?
I think because there's so many people in this course, the easiest way it would be to come to the afternoon session on Friday if you can. If you can't, if you have a conflict, many of you TA, then email Max. No, if you do email us, then copy the other person. So that way we're not, don't ask the same question to each of us without copying us.
Yeah.
So that way we won't be duplicating our efforts. And then there's a question here, and then there, and then there.
How do we sign up for individual office hours? Is it just by email?
I will send out an email probably on Saturday or Sunday to tell you that. I think the individual one-to-one office hour will start on Monday, so I will send out a specific instruction on how to sign up for that.
So typically what we'll do is it's a Google Doc that people can just sign up and edit with office hours, and they'll be posted. They'll be provided about 24 hours before they're open, so that way everyone has an equal chance, and you don't book the week in advance. There's a question here?
She has.
Ah, excellent. And then there was one more.
Yeah, will the review session on Friday be recorded? So
Yeah, sure, we can do that.
Cool.
Okay. All right, go team!